So, in previous class we are dealt something about the introduction of organic photochemistry. What we will do in this class, we will also deal something more about the introduction part, because we left up to R star, right. If you see in our previous class, we discussed that you have an R which is your ground state reactant, gets interaction with your light which is your reagent, gets excited, we call this as an excited state reactant. We said that it can go to your singlet state, then it undergoes an intersystem crossing to give you a triplet, which then gives you an I. We said it is a short lived intermediate, which gives you the P, which is your isolated product. So, this was we studied in detail, or we just brushed up like how your R can be converted to your P. Then we went inside and studied in detail how R is getting transformed into R star. So, that was what we discussed in the previous class. Now, what we will do is that we will just put little bit insight into how this R star gets into R star triplet. So, like we will try to understand the energy levels of the singlet and the energy levels of the triplet, what is going to govern why this molecule has to go from singlet to triplet, is energy level of the singlet and triplet have any meaning on that. That part we will do today, like we will just start with that, fine. So, we will be concentrating now on how R star singlet is undergoing an intersystem crossing to R star triplet. So, we said that you have an S0, you will be having an S1 and you will be having a T1. So, your S0 can go to S1. Okay. Now, this S1 can come back to your S0. It has an option of doing two things, right. It can come from S1 to S0, or it can do an intersystem crossing to your T1. Now, it has option of doing two. Basically, the intersystem crossing, if you see, depends upon the energy gap of your singlet and triplet. So, it is one of the factor. If the energy gap between your singlet and triplet is very small, then what happens? The molecule try to undergo an intersystem crossing rather than doing your photophysical. There are many other criteria like lifetime of your singlet and triplet, but now we will concentrate only on the energy gap. If your energy gap is small, this molecule try to do an intersystem crossing rather than doing the photophysical things, right. For example, we will take an n pi star. So, I have my S0, I have my S1, I have a T1. This is for my n pi star I am drawing. This is n pi star transition. So, I have a S0, S1, T1. On the other hand, what I am going to do, I am going to draw for my pi star. So, I have an S0, then I have my S1 and I have a T1. Now, if you see or if you notice that I have drawn that energy gap between singlet and triplet to be little bit smaller, okay, when you compare to the energy gap between singlet to triplet in pi star. In n pi star, the energy gap is small, when you compare to the energy gap of your pi pi star. This is little bit small and large. So, now what we will see is that small large what it means, okay, we will see by numbers, okay, then we can understand how small, how large it is. For example, I will take a ketone. Okay. If you see the singlet energy level of ketone, it is most of the time it is 80 kilocalories per mole. This energy singlet one, this is 80 kilocalories per mole. And if you see for your triplet, that is 75 kilocalories per mole. So, you have an energy gap of only 5 kilocalories per mole. Same way, if I go for my pi pi star and see what happens, what is the big number there. I draw for my benzene. Any idea what will be the energy level of the singlet for benzene? Anyone? So, it 110 kilocalories per mole. Okay. If I go for my triplet, it is 90 kilocalories per mole. So, this can be 90 to 80 depends upon yeah, it will be 80 kilo, if it is 80, sorry, it is 80 kilocalories per mole. So, you have an energy gap now of 30, right. Same way, if I draw for naphthalene, it has of energy of 90 kilocalories per mole singlet, and your triplet is 60 kilocalories per mole. If I draw for anthracene, it is 70 kilocalories per mole, and for this it is 40 kilocalories per mole. So you see the energy gap now. For n pi star transition, the energy gap is only 5 kilocalories per mole. But if you go for your pi pi star transition, it hangs around about 30 kilocalories per mole. So, what I can say from here, when I do n pi star photochemistry, okay, my photochemistry will be most of the time dominated by my triplet, right. I can see my photochemistry happening most of the time from the triplet state, because all the molecule gets excited to singlet, then since the energy gap is very small, they all undergoes the intersystem crossing to give me triplet. So, I see all my photochemistry happening from the triplet. But when I come to my pi pi star, so what I can see? Any idea? I can observe photochemistry both from singlet as well as triplet. So, pi pi star chemistry, most of the time you can see photochemistry happening from the pi like singlet state as well as my triplet state. So, molecule, some of the molecule tries to do intersystem crossing and then do the chemistry from triplet. Some of the molecule says I am happy in the singlet because I cannot jump 30 kilocalories. So, I can do my chemistry from singlet state. That is why this energy gap matters a lot in deciding the photochemistry from which state it occurs. Clear? Now, what we will do is that now the next question comes in the mind, why n pi star energy gap is small and why pi pi star energy gap is huge. When you talk about why the energy gap between n pi star is only 5 kilocalories per mole, but when you go for a pi pi star it is 30 kilocalories per mole. So, for that what we will do, just we can understand based on your orbital picture. See, if I write about, I am taking for, I will write for first. So, I am trying to draw triplet of pi pi star. So, I have an electron here, I will have my electron like this. This will be my pi and this my pi star, right. So, what happens? You will get a very good repulsion. So, repulsion between your pi to pi star will be large. Okay. When I draw for my n pi star, if you just watch our, if you draw for my n pi star, so now you can see the repulsion in n pi star, right. So, your repulsion in n pi star should be, in this case, very less. When you go for your pi pi star, it will be high. That is the reason why your n pi star energy gap is only 5 kilocalories per mole, but when you go for a pi pi star, the energy gap becomes more, right. This is the reason. Just by orbital you can know, by repulsion. Clear? So, we can say that now we have at least some idea how this R star singlet is getting to R star triplet and how they dominate over your photochemistry, whether the chemistry has to take place from triplet or the chemistry has to take place from singlet or either singlet or triplet. This all depends upon the energy level of your singlet and triplet. There is another feature which we will slowly consider, will be your lifetime of your singlet and lifetime of your triplet, that also will come into the picture, but right now we will think about the energy level. That is the first criteria. So, that is good. So, now we know how to move from R to R star in detail. Now, slowly let me understand how we are going from my R star to your nest I. That is your next step. How this R star is going to get into I. As I said that once a molecule gets excited to your excited state reactant, that is your R star, it can undergo some major sort of chemical reactions, like your R star can do an atom transfer, it can do an electron transfer, or it tries to do your bond breaking, it can break a bond or bond making, or you can bond formation or bond making, whatever it is. So, these 4 things can occur from your R star. Your R star can do either an atom transfer or it can do an electron transfer, it can break a bond or it tries to make a bond to give you an intermediate I. So, what is this intermediate actually? The first thing you have to remember most of the time you go wrong is that, see, the intermediate formed is again a ground state species. The intermediate is not an excited state, okay? It is a ground state species. You know that a ground state species most of the time is singlet, right, that you know, except your oxygen, most of the time ground state species are singlet, remember that. So, it forms a ground state So, now the question you ask is that why we are not able to isolate this. This ground state species is so reactive, okay? Like it does an intramolecular hydrogen abstraction within itself, or it can do an intramolecular hydrogen abstraction from outside, inter or intra. So, the reactivity of this I is so fast, okay? So, it forms me the stable product P. That is why we are not able to isolate this I, but it does not mean that this intermediate is in the excited state. This intermediate is a ground state intermediate. So, the best example for that is your carbene. You can have your nitrene, you can get free radical, biradical, radical ion, like carbocations, carbonium, all these things will get into a intermediate species. So, this is your I. Yes, sir. Okay. So, same way if you see the energy profile, how it looks like. See, I have my R star, it goes to a transition state, then gives me an I, then it goes, then it gives me a P. So, this will be my transition state, this will be my intermediate I am talking about, okay, and this will be my product, right. So, where your intermediate stops, that is the idea. So, it says that my product is still in lower energy, that is why this is the isolated product, not this guy, that is why I am saying. So, this will tell you this energy profile that it is not the really stable product which you can isolate. The important thing now to remember in this intermediate is that the spin of your intermediate most of the time will be exactly same of the your excited state reactant. What I am saying is that, see, I have R star, okay, which is from the triplet, and you know your intermediate is what? It is a ground state species and it should be singlet, but it does not happen like that. What it does, first it forms you an intermediate of triplet, then your triplet intermediate then changes itself to singlet. That is why I am saying the spin is most of the time is same as that of your excited state reactant. This is very important thing, because your intermediate spin most of the time will be the spin of your excited state reactant. It does not have much time to flip around to give you a ground state species. So, your reactant, excited state reactant breaks and gives you the intermediate. It does not have a time to flip around the electrons to give you the ground state. The ground state intermediate then changes the spin to give you a ground state singlet. It is clear. So, for if you are getting from an R star from the singlet, I said in pi star chemistry you can see photochemistry from the singlet also. In that case, you can directly get your intermediate of singlet. That is why I said that intermediate, the spin of your intermediate most of the time are same of the spin of your excited state reactant. Clear. So, these are the points which you have to remember when you move from R to I. First, I said that your R star can do some sort of reactions which will be your atom electron transfer, then your bond breaking, bond making to form your I. Then I said your I is a ground state species, but it is very short lived due to its reactivity. And then I said that the spin of your ground state, spin of your intermediate will be most of the time exactly same to the spin of your excited state reactant. Clear? This is how you change from your R star to I. Now, what we will do is the final one, which is the most of the time the simple one. it is your I to P, which you have studied, because you know, because this is mostly a ground state reactivity which you have studied, I to P. The two points you have to remember when you transform from I to P is that, one, the I to P can be a single step, or it necessarily need not to be a single step. It can be multiple steps. That is the first point you have to remember. It doesn't need to be, not to be single step. So, your I can transform to P like this, or your I can do a multi-step process to give you the P. The second point you have to remember when you talk about I to P is that this is most of the time happens in the photochemistry, that your I will not give, it is not necessarily that you have I has to give only one P, that is one product. I can give you different products. So, you can get more than one products when you transform from your I to P. These are the two things you have to remember when you talk from I to P, intermediate to product. It can be a single step or it can be a multi step. You can get not only one product, it can give you to several products, right. Yes. So, this is what we look for from R to totally to your P. Now, what we will do? We will take all this idea and summarize them together and say this is the big idea of the photochemistry. We can represent simply by words, then we will do some orbital, that is also simple, that we will do. First, what we studied, we have an R gives you a R star singlet. R star singlet will give me a R star triplet, which can give me an intermediate, and that will give me a product P. If you write with respect to your LUMO and OMO just by electron spin, okay, then I can write like this. For example, I am talking about so what you get first, you get your S1. So, your spin most of the time will not flip, right, that is what you studied in the Frank-Condon principle. So, that will be your S1. Then it undergoes a sort of inter-system crossing to give you your triplet. For example, I consider this R star, that is a triplet R star, is trying to undergo a bond breaking process, bond breaking, okay. You are breaking SEC bond or whatever. Then I can write my intermediate like this, like I can say it is a p orbital of C1 and p orbital of C2, okay. So, but see the spin what I am maintaining, I am maintaining a triplet spin, because it comes from the triplet R star. So, I am getting a triplet I. So, I can say my I is triplet. Now, what happens, this triplet I makes a spin flipping to give me a singlet I, to give me my final product P. Okay. So, this we will call as a big idea of photochemistry. Any doubt up to this? Okay. So, what we will do now, we will take a reaction, an organic reaction, and see that how we can represent that by a simple representation of photochemistry and big idea of photochemistry, how we are representing. For example, I am taking a ketone. Photolyze this part. Basically, I am doing it around 310 nanometer. Okay. So, what happens? Get this one product and you get. So, this will be your simplest representation of your photochemistry. Like what we said, you have an R star, you have an R, this is your ground state R, and you have your ground state P. So, this is the first we started our class. We said that this will be your simplest representation of your photochemistry. If I want to see in a big idea how this R is converted, then we can write the same reactions like this. So, how I write? I say that H mu, this is my R. I am doing a sort of n pi star transition because I am shining a light of 310 nanometer. So, my carbonyl gets excited. Okay. So, you can write this as a singlet. Okay. R star, first it happens to be your singlet, right, or you can put like this your singlet with an excited ketone. You can write like this also. If you want to put your spin, you can put also take the bond and you can put the spin. Put a triplet here, R star triplet, you can write like this. So, you know what happens. So, it forms then so you get a intermediate I. So, this should be a triplet intermediate. Yeah. So, from here I told you that this I can give you different products. So, for example, you can make this much more legible, like I can can get this stage, then it picks an hydrogen from here. You can make this as your I. So, you can make this as your I, not this. This will be happening in your triplet state itself, right. This you can call as a triplet spin. If I put the spin, then it will be a triplet. So, you have your I now. So, what is this I? It is a nitrene or carbene or diradical, what it is? It is a 1,4? 1,4, right? 1, 2, 3, 4. It is a 1,4 diradical. So, you know what 1,4 diradical does? it can cyclize give me this product, or what it does? Bond breaking. What bond breaks? Here it breaks this bond, all right. Then it undergoes a type ketone alpha terminalization to give you your ketone plus it gives you your alkene. So now you have an I. This we call as one product. You can call them as prime, P, double prime. See, this is my ground state product, which I can isolate. So this is a simpler representation. So you have an R gets excited to your R star singlet, then it becomes R star triplet. I have written it in this way. It's not an equal. It should be like this. So it says spin. I have written the spin for your triplet, and then this can abstracts an hydrogen to give me an intermediate, which is a 1,4 radical that can do ground state reactivity. One, it can cyclize, or it can undergo a bond cleavage to give me this product. So that is how we can represent a organic photochemistry. This is the first one which I showed is the basic representation. How you want to represent? You can represent just R and T, okay, or you can. This is the big idea of saying the organic photochemistry. Okay. So one more thing you have to know before we finish the introduction, that is your yield, quantum yield. Okay, that part you should know. So you know what is a chemical yield basically, right? Because most of the time as a chemist you know what is a chemical yield, right? I have an, for example, you have an R, it gives you P. So how you know this reaction? How you say this reaction is 100%? It gives all my R is converted to P. How you say that this reaction is 100% based on chemical yield? How you say? No, I am not talking about quantum yield. Just an organic chemistry, you are taking a substrate, you say that the reaction is 100% based on chemical yield. How you say? Hmm? No, no, with respect to chemical yield. So you take a 1 mole of your, if you take 1 mole of reactant, so when you say the reaction is 100%. So you take 1 mole of your reactant and you should get 1 mole of your product, then you say the reaction is 100%, right? That is just a chemical yield. For any reaction it is. But once we go to the photochemistry, you have an R. So same way I can say, if I have an R, okay, I take 1 mole of an R and I get my P completely, that is my R is converted to my P. Then I say this reaction is 100%, right. So I say it is 100% based on the chemical yield. So your reaction can be 100%, but the important point here in organic photochemistry is that most of the time we are not call a reaction its efficiency based on chemical yield. Most of the time we talk the efficiency of an organic photochemistry based on its quantum yield, that is based on the photons. See, if I have an H mu, that is my reagent, right. So if I take whatever like 1 mole of photon or whatever, how much of product I am getting, then it will be my quantum yield. See, when I talk with respect to my reactant, then it is chemical yield as your chemistry, general chemistry. But once I talk with respect to my photon, okay, then the point of quantum yield comes into the picture. This we call as quantum yield. So, you have to talk with respect to h mu. Okay. Now, the question comes is what is quantum yield? So, you use this simple for quantum yield, right. So, you say anyone what is quantum yield? So, number of product molecule formed. See, your quantum yield can, most of the time we calculate the quantum yield based on your product. Okay. You can also calculate the quantum yield with respect to your substrate also. But if I have like 2-3 products, so it is better that I calculate with respect to my product, right. So, number of product molecule formed divided by number of photon absorbed. So, that you call as quantum yield. So, the question is why this is so important, why we can talk with respect of chemical yield and leave the chemistry, right, why you want to talk with respect to your quantum yield. See, I have now my R giving to me to R star and my I and my P. As I said that if my R gets completely converted, it is fine that it is an 100% chemical yield. But you see, if I take 1 photon and this 1 photon transfers my R to R star, okay. But what happens to this R star? This R star can give me my R back. There are chances, right, this R star coming to give me the R. So, what happens, and same way my I also can give me the R back. So, what happens if I use like 3 photons for example, just for 3 photons, or you can say 1 photon. So, I am using some photon for this reaction, okay. Same amount of some photon I am using for this, and I am using, for example, I have 1 photon, I cannot correctly divide, just by numerical I am saying I have a 1 photon. So, I will be using 0.33 for this process, right. So, and another 0.3 for my I to R, and another 0.3 I will be using for R to P. So, the reaction might be 100%, my all R is converted to P, that is fine. But if we talk with respect to photon, what happens? It is only like the reaction has been only your 0.33 photon has been used for converting your R to P, rest of them it has been inefficient. Okay. All your, what happened, all your R star went to R and did photophysical property, came back, or your I again reback and gave me the R. So, what happens, I am use this photon of nothing, not for converting my R to P. So, we call these steps as inefficiency step, okay. R to R, R going to R star, then coming back to R, R going to I and coming back to R we call as inefficiency step. That is why most of the photochemistry may getting your quantum yield 1, getting your quantum yield equal to 1 will be really hard, most of the photochemistry reaction, because you know that all the time when the molecule goes from your R to excited state, it has a competition, it can do its photophysical or it can do a photochemistry. So, you are not going to convert all your R to R star. So, people you can say that quantum field can be any number, it can be any number, it can be a fraction of any numbers. Okay. But having a quantum field of 1 most of the time is hard. Okay. It's very hard process. There are processes which have, but you do not see much. Okay. Some cases you see quantum field greater than 1. In some process you see quantum field greater than 1. What are that process? Yeah, you do have polymerization type of reactions where your quantum field will be greater than 1, right. That is good. How to so your quantum field will be any number, okay, I can say it can be any number, quantum field greater than 1, you can observe it in polymerization reactions or chain reactions. Okay. Now, one more thing is that how to calculate this quantum field. There is actinometers which we call, okay, you can use a actinometers. There are actinometers available, or you can use actinometers like reaction based actinometers you can use. For example, you know valeriophenone chemistry. Okay. So, what you do is that you take a valeriophenone and do its chemistry, and you know for this much of light how much valeriophenone you should get. So, you keep a valeriophenone and on the side by you keep your reaction parallel, and then you can compare, and from that you can find out your quantum field. So, most of the time we use actinometer to calculate our quantum field, but that part I will explain you when we go for the experimental section. There are many instruments which we can use for actinometer. There are solutions which are available, that I will list it out, and it depends upon the wavelength. If you are using 410 nanometer, then you have to use different type of actinometers. When you use for 310, so it depends upon the reactions, and there are solid instruments which can directly find out the light. Okay. So, that part we will be discussing, but you should know quantum field you can calculate based on your actinometers. Right. There is one more part like which we have to see is there are some product inefficiency steps. Like I said, there is an inefficiency step of your R to R star. There are one more part which we will call as product inefficiency step, that also will be involved when you do some quantum field calculations. Okay. That is very simple, like you have an R, it can give you an R star, and this R star can give me I and then P, right. See, it is not that my R star is going to give me back my R, does not mean that it has to always give my R. Sometimes what happens, your R star can also give me another intermediate I prime, that also happens in photochemistry reactions. Okay. So, this I, it does not need to give me back my R. Okay. This I can give me I double prime also. So, I can from I prime I can get my product, another product which we call P prime, and I double prime we can get another product we call as P double prime. So, we call this as another competitive product inefficiency steps. So, see, if you want to do the quantum field calculation, in this case what you will do, if you want to do a quantum field for your reactant, so you are saying number of reactants divided by your number of photons, that time what happens, you go wrong. because you are getting different products now. So, in this case we will try to do the quantum yield based on your product. I will say the quantum yield for the product P is 0.335, okay, and the quantum yield for the product P double prime is different, and the quantum yield for the product. So, here that is why I said it is number of product molecules divided by number of photons. If the reaction is a single step, that it gives R to P, only one product, then you can talk number of product molecules or number of reactant molecule disappeared divided by number of photons. But there are very few cases where an organic photochemistry R gives you to P. Most of the time if you do an photochemistry reaction, you get like n number of products. So, that is why it is safe to calculate your quantum yield with respect to product molecule rather than reactant molecule. Clear? So, that is because that is what the another point you have to remember in quantum yield. So, your what I said is that your on organic photochemistry you never you can calculate with respect to your chemical yield, but that is not so much better way to do it. So, we calculate with respect to your quantum yield, that is the first point we said. Then we said that quantum yield is nothing but it is a number of product molecule divided by number of photon absorbed. Then we said one point again, your quantum yield can be any number. It is very hard to find out number 1, okay. Quantum yield equal to 1 is very hard. There are many reactions where your quantum yield is greater than 1, that is your chain reactions, polymerization reactions takes place. Then we studied there is an inefficiency steps happens, that is why you have to calculate with respect to your photon rather than talking about the chemical yield. Then we said there are number of you have to calculate with respect to product molecule rather than with respect to your reactant molecule, right. So, that is how we did quantum. So, I think the introduction of organic photochemistry, you can finish your introduction with this, and then we will what we will do, we will start now. The introduction part is over, organic photochemistry. Now, we will start getting into the reactions slowly, like what are the reactions this. We will take organic molecules and try to understand their reactions. So, the introduction part, most of the introduction part is over with this. Any doubt on the introduction part? Because that is all, it is over introduction. I do not want to any point you guys want to ask, like previous class what we did, how we moved from R to R star, because you are studying your UV spectroscopy class also. So, you should know that how we any doubt there into R to R star transition, because that part is very important, your R to R star. When you shine a particular light, what type of transition I am going to look for, whether I am going to look for an n pi star transition or I am going to look for a pi pi star transition. Then you talk about your singlet and triplet there, okay. Any like the energy gaps, lifetime, okay. After that you talk about your intermediates and then your final photo products. I want to know that if you have any doubts, we can just clarify now itself before we enter into the reactivity, because next I am going to take reactivity of n pi star chemistry, organic reactivity of n pi star chemistry. So, what we will do is that we will see, we will start organic reaction of n pi star, and we will see the all the reactions of n pi star, what n pi star transition can do, what are the reactions, and then we slowly go to the pi pi star reactions and see what are the reactions pi pi star can do. Your pericyclic reactions will get into this pi pi star scheme slowly, okay. N pi star may you do not see any much reactions happening. Any idea what n pi star reactions takes place, what are the reactions n pi star can do? What type of reactions? I am not molecules. N pi star chemistry. If I take a carbonyl, for example, I take a carbonyl molecule, shine a light of 310 nanometer, Okay. So, you know that it goes to singlet, then it undergoes an intersystem crossing to triplet. So, after that what are these reactions normally you see? What are the chemistry you can think what my triplet n pi star can do? Yes, come on. Huh? It does dimerization, little bit less. Pi star does dimerization, right? You can see any other good chemistries. Any other good chemistry? Okay. So, what I will do is that I will leave with this. You can have a break and then we will have in this class. Okay. I will start about n pi star chemistry. We will see what other reaction these guys are doing. Okay.